the add instruction in this AVR processor. So, it may be like add RD comma RR, where RD is the destination and source in the register file, and RR is the source register in the register file. So, it will be the operation that will happen is that RD will get RD plus RR. So, this is the destination and source, and the second register is the other source. So, this way this add instruction may be executed. So, for example, this add R23 comma R11. So, this will be given as a 16 bit code 0EEB, and the bit pattern coding is like this. So, out of that this 5 bits, so 00011, so they will correspond to add instruction. Then next 5 red bits, so this 10111, so they will give the register number 23 as the first operand, and then this 01011, so that is 11, so that is the second second operand of the register. So, this all RD/RR instruction will follow this pattern. So, this has got a coding like this. So, this 0 is redundant. So, this 0 is extra, nothing is there. So, that is taken as 0. So, all instructions will be coded like this. So, if we are looking into addressing modes, so then there are different modes, like we can have register direct with 1 and 2 registers. So, we can directly specify your operand as a register, or you can have IO direct. So, you can have some from the input output port addresses. The data direct, data indirect with pre, and data indirect can also be with pre decrement, post increment type of thing, and code memory addressing. So, we will see these addressing modes. Register direct, one register, like say increment R16. So, this instruction, so this will increment the R16 register. So, this is a 16 bit instruction. So, in the register file, so R16 is given the number, the corresponding index is D. So, the opcode part will be there, and then this D, these 4 bits will identify the register on which you want to do the operation. So, this is D. So, in the current register bank, register 16 will be incremented, or say clear 22. So, based on that 22, so it will be the destination will be coming. So, this D is the number. So, for this case this D will be 16, for the second instruction D will be 22, for the third instruction D will be 0. So, it will be like that, but 4 bit coding will be sufficient to differentiate between the 16 different registers that we have. Now, you can have register direct with 2 registers, like this add instruction, add R6 comma R17. Here we will have this register direct and this RR and RD. So, both may be there, and they can be used for again we can have 2 registers mentioned here, and the indices stored as part of the instruction. So, this is also a 16 bit coding. So, register direct with 2 registers. IO indirect. So, you can say that okay, it is in R16 comma PIND. So, PIND it will identify some port number. So, this will be so this P will be identifying. So, this is the opcode part which is say in, then say R16. So, this is the register now, this is the register number. So, this will be coming to this N, and this IO memory. So, this PIND. So, this will, as there are 64 IO pins as we have said. So, it is the it is a 64 IO locations that we have seen. So, we have it is from the 60 whatever be the port number we have identified. So, from that port the value will be put into this corresponding register. So, from this particular port the value will come to the register R16. Similarly, out port C R16. So, it will output this R16 value onto port C. So, again that port C will have some address, and accordingly it will be selected. Then data direct. So, you can say like the STS instruction. So, stored data stored direct to data space. So, here so we have got this opcode which is that STS, and this register, which register will be acting as the source, and that value will be going to this destination. So, this LS this address is a 16-bit address, and this 16-bit address will be used, that will be part of the instruction, and this R16 value will be copied onto that particular address. So, this is a 2 byte this is a 32-bit instruction. So, 0 to 32. So, previously we had all 16-bit instructions. So, this is 32-bit instruction. Then we have got data indirect. So, you can there are 3 registers, as we said, X, Y and Z, and these registers can be used for indirect addressing. So, you can say like load R16 comma Y. So, wherever Y is pointing to, Y register is pointing to, so that location's content will be copied onto R16 register, or store Z comma R16. So, Z is another pointer. So, whatever be the value of R16, so that will be stored into the memory location pointed to by the Z register. So, we have got this X, Y or Z register working like that. You also have data indirect with displacement. So, it is a load with displacement LDD. So, this is R16 Y plus some constant value 10. So, Y register, with that this 10 value which is coded here will be added, okay, and that will act as the offset where the value should be written. So, if this location content is a 1000, so with that this 0 will be, this 10 will be added. So, it will become 1010, and then that location content will be updated. Similarly, we can have STD, where we have first we mention this indirect register plus the offset, which is say 0x20, and that value will be, so there will be storing the value of register R16. So, this way we can have this data indirect with displacement. There is another mode, data indirect with pre-decrement. So, data indirect with pre-decrement, here it is LD, there is no displacement. So, there is the LD, D part is missing, D is not there, only LD, R16. So, it is, so in R16 will be loading the value pointed from the memory location pointed to by the Z register, but before that Z will be decremented by 1. So, it is pre-decrement. So, Z value will be decremented, and then that address will be used to access the data memory. So, this is minus Z, or you can have this pre-decrement ST minus Z R16. So, you can decrement before accessing the location, and first R16 value will be stored in the memory location pointed to by Z minus 1, and simultaneously, so Z is decremented by 1. So, you can have post increment also. So, it is Z plus. So, this Z register value will be incremented, but the previous value of Z register will be used to access the memory. After that, this Z register content will be incremented by 1. So, this is the post increment mode, and we can have similarly for storing also we can have post increment STZ plus R16. So, that way we can have this value stored in the memory location pointed to by Z register. After that, this Z register content will be updated. So, we can have this data indirect with post increment. So, we have pre decrement and post increment. We do not have post decrement or pre increment. So, those modes are not there, but pre decrement and post increment, these are the two modes that we have with data indirect mode. Some other interesting instructions, like we have got this NOP, we do nothing for 1 cycle, then sleep. So, sleep until reset or interrupted. So, sleep instruction is there. Then watchdog reset. So, as we are discussing while talking about that PIC microcontroller, so we have got watchdog timer. So, here also we have got watchdog, and there is an instruction by which you can reset that watchdog timer. So, you can say like WDR watchdog reset, that can be used. So, for the IO pins, so these are general purpose IO ports, and each port has 3 control registers associated with it, DDRX, port X and pin X. So, the DDR register is the data direction register. So, it will tell whether a pin will act as an input pin or an output pin. So, it is if it is 0, then it will be an input pin, and if the bit is 1 in the DDR register, then it will act as output pin. Then the port, so it is pin will act as output or it will be a read operation, and then the read tweak. So, we will come to that, and there is a pin. So, there is a pin can be the port port input. So, this register is read only. Okay. So, that way we can have different configurations. Then there are IO pins and packages. So, 15 programmable IO lines are there. So, that can be used for input output operation. As far as timers are concerned, so it has got 8-bit timer, and these timers are wraparound up counter. They can be configured as wraparound up counter. So, after the overflow, so it will be coming down to 0, and from there it will be going, and there will be an interrupt controller. So, there is an interrupt on the overflow, like if when the timer or the counter overflows, then this interrupt will be generated, and it can be told, the processor can be told that an interrupt has occurred. So, this diagram, so this is one pin diagram for this Atmega 16 processor. So, you see that you can have a number of ports like PA0 to PA7 as ports, then PB0 to PB7 as port B. So, there are 4 such ports, PA, PB, PC and PD, and so there are timers like T0 and T1, there are 2 timers. Then we have got analog inputs 0, 1, so for this analog input. Then there are some special lines that you can see here is the MOSI, that master out slave in, and MOSI, MISO, then this SS bar and SCK. So, these are used for some special communication, serial communication, which is known as SPI or serial peripheral interface. So, it is like this. So, this serial peripheral interface or SPI so it is a very simple type of interface where between the processor and device. So, so there is a master and there is a slave. Okay. So, this is the master and this is the slave, and the data transfer is very simple. Both the master and slave, they have got one register, this is, they are called SPI register. So, this is the, suppose this is the SPI register in the master. So, this is an 8-bit register, and slave also has got one SPI register which is 8-bit. Fine. Now, there is a pin which is master out slave in or MOSI, master out slave in. There is another pin master in slave out, okay, master in slave out. So, from the master side you can say it like so you can see it like this. So, then there is another pin which is slave clock. So, this is slave clock, and there is another pin which is slave select. So, this is the configuration. Now, when the data transfer will take place, so this is a synchronous transmission, and this whole thing is controlled by this this slave clock. So, the master will be giving the clock and the transfer will be based on that, and the transfer that happens is basically an exchange. So, this transfer that takes place is an exchange of these 2 register values. So, there is no direction of transmission. So, it is always bidirectional. So, this SPI value will be going through this MOSI line to this one, and this value will be coming through this MISO line to this one. So, that way there is an exchange between the 2 content. So, this is a very simple type of protocol, and many of the embedded systems, they use this type of protocol, because the interfacing devices that we are going to connect. So, they are going to be very simple, and they do not support say very complex communication protocol, and so this serial peripheral interface or SPI. So, this is used. So, it is a very simple protocol. Okay. So, you can always support in a microcontroller this type of protocol, but in Atmega series you see you have got this thing directly implemented. So, you have got this slave select line, the MOSI, MISO and this slave clock. So, they are useful for doing this for SPI type of interface. Another interesting interface that we have here is via this SDA and SCL line. So, this is these are for another type of interface which is known as I square C interface. Okay. So, they are for this I square C interface, integrated circuits. Integrated circuit, they have got the name IIC or I square C or I2C, there are various names. Okay. So, here what happens is that we have got two buses, one is called this SDA and another is called SCL, and then we have got these devices that will hang from these buses. So, every device has got one connection to SDL and one connection to SCL. So, it will have like this. Now, when the communication takes place, so this master, so if this is a master and these are two devices, then this master will put this device address onto the bus, and the device which will be which will have that address. So, this will be sensing that value, and then it will be the next byte that will follow. So, there is a serial transmission. So, next byte that will follow. So, that will be taken by that device. So, this is a two-wire interface where we have got only two lines SDA and SCL, and it is a serial transmission. Okay. This is a serial transmission, but we can have multiple bus masters and multiple bus slaves that we can connect to this system. So, this may be master 1, this may be master 2, and there is a protocol by which it will detect that there is a collision or something like that. So, there are various such things are there, various protocols are there in I2C, but still it is much simpler compared to a full fledged communication protocol, where I will have a number of devices hanging from buses, there will be bus arbiter and all those. So, those things are not there. So, this SPI and I2C, they are two very simple interfacing standards, and in ATmega series of processors, so you will find them. Okay. So, they are useful so for connecting some simple device to the system. So, the many of these devices like say real time clock module, then this ADC modules, then this small memory chips. So, they are having this SPI or I2C interfaces. Okay. So, that way the design becomes simpler for those chips, or if you are designing a sensor, maybe we do not bother much to have a very good interface with that sensor, and that sensor may not have, say for example, USB interface or RS-232C interface like that. So, it can simply support one of these interfaces, and that device will be able to talk to this ATmega series processor. So, we have got this timer counter 0, it is 8-bit up counter, it counts from 0 to 255 and then loops back to 0. The clock source can be internal or external. So, when it is a clock source, so it is a timer, when it is a clock source is external, so this is a counter. There can be a prescaler, so you can initialize this timer value to some initial value. So, that way it can start counting from there. Then output is captured through OC0, that is PB3 pin 4. So, if there is an output overflow, so that will be captured by that. It will also generate an interrupt on overflow. So, whenever it makes a transition from 255 to 0, you can make it to trigger an interrupt. Okay. So, you can make it to trigger an interrupt, just like in 8051 we have seen that the timers can be programmed so that the interrupt occurs. So, here also the same thing, you can make the interrupt to occur. So, OCO is the output compare. So, this is the output compare match output. So, it when the output matches, whenever this TCNT 0 will match with OCR 0. So, there is the output compare register 0. So, there will be this value will be saved there, and whenever this count value becomes equal to this OCR 0 register value, output compare register value, then this output compare match will become enabled. So, this can be used to serve as an external output for the timer counter compare match. So, internally this is the timer is doing something, and if you want to detect some particular point of occurrence, you can put the desired time values in the OCR register, and then you can observe this OCO pin. Okay. So, with the OCO pin say whenever this value, the timer value will match with that OCR 0 register, then this timer counter 0 compare match. So, that output will be made high. So, to the external world you will know that there is a match in the current value. So, we can use it for triggering many other operation, maybe in some other devices. So, we can trigger some operation. So, it can be used for that purpose. Then we have got another timer, which is AVR counter, timer counter 1. This is a 16 bit timer. So, there are dual comparators A and B. So, for output comparison, it is a up counter. It provides an interrupts on overflow. It compare with A, B. So, if the comparison matches, then also an interrupt will be generated, and this input capture of external event on ICP pin. So, there is an ICP pin. So, if there is some external value that you can want to match. So, you can external event can be taken through the ICP pin when it is working as a counter mode. You can also be used to act as 8, 9 or 10 bit pulse width modulation applications. So, if you want to modulate some pulse width for transmission, so you can use it in up down counter mode in 8, 9 or 10 bit pulse width modulation. The input capture unit of timer or counter, it will capture external events and give them a time stamp indicating the time of occurrence. So, this is one important facility that it has. So, you can get the time stamp of occurrences of the events. The external signal indicating an event or multiple events can be applied via this ICP1 pin or via the analog comparator unit. So, that way you can give these external signals to the AVR microcontroller. So, time stamps that we have got, so we can use it for calculating frequency, duty cycle or other features of the signal. So, it is like this, some signal is coming. So, we are trying to capture some feature of the signal. So, at different, so as the values of the signals are changing, so we capture the values of the signal, and from the timer counter module, so we can get the corresponding time stamps. So, later on we can use it for getting the frequency or some other features of the signal. So, that can be used for some other application, so for signal processing application. Alternatively, so they can also be used for creating a time log, like say if there is a telephone call, so how long the call has taken place. So, you can start when the call is starting, so you can have the timestamp stored, and then when the call is ending, you can again get the timestamp. So, internally this timer is running, so you can get the timestamps from there, and you can get an information about the duration of the call. So, this way this time stamping feature can be utilized in different applications. Then in timer 1, so it has got two output compares OCR 1A and B. So, they are 16 bit registers. Okay. So, when the value of this OCR 1A or 1B matches with timer 1, so user defined action can take place on the OCA or OC 1A or 1B pin, like we can set or reset or invert the pin. So, you see this is a very interesting thing, like if whenever this matching will occur, so you can program the system so that particular pin will get set or reset. Maybe this is connected to some LED, that LED will glow, that that match has occurred, something like that. And interrupt can also be triggered, and timer 1 can be cleared to 0. So, either you can, so in other processors what was happening is that for example, in 8051, so if a timer starts, and when the timer overflows, then it gives an interrupt, and that way. But in between time values, so if you want to get some stamping, like if you want to get some notification in between, that is not going to happen. So, you have to stop the timer with that time value, then only you can get that notification. But in this case it is more flexible, because I can have this timers programmed in such a fashion that when that time value reaches a particular value set in the OCR register, so we can initiate some action, like setting clearing bits, or setting an interrupt, or stopping the timer by resetting it to 0. Once set up, the output will compare the output compares operate continually without software intervention. So, you just have to tell that I need to compare this. So, once that is done, so it will be continually doing. So, it precise recurring timing. So, this can be used for recurring timing, say when the event is occurring again. So, you can find out frequency or tone generation for sound effects at some particular frequency you want to generate some tones. Okay. So, for different I may have a number of sound different number of different sounds to be produced, and each of them will occur at some different periodic boundaries. Okay. So, that way I can do that by controlling this output capture part, and then the digital signal generation like infrared communication, then software driven serial ports. So, wherever we need some sort of periodic thing to occur continually, like in 8051 we had that mode 2 where it was a auto reload type of operation, but here it is not required. So, here it is you can do this OCR and this output timer 1 for doing this operation.